Okay, so thank you very much for the nice introduction and for the invitation and the opportunity to give this talk. Yes, as Daniel said, please feel free to ask questions at any time, and I'm happy to answer. So today, I wanted to talk a little bit about some of the work I did recently, but I do understand that this audience is very broad and maybe there are not so many experts in cosmology. So the idea here is really to give some very broad overview of some of the things that I've been doing recently without going into too many technical details. So I will start with some broad introduction and context, do some quick review of some standard cosmological analysis. Why are they important and how do they work, and what is coming in the near future. And then I want to contrast this to something which is more not so well tested so far, and some different new approach to analyzing cosmological data, and this is the field level inference, and explain that what is the status and what are some puzzling features at the moment that I think would be very interesting to resolve. So let me begin by something that you have all, I'm sure, seen many times, and this is, of course, the observations of the cosmic microwave background radiation. We're measuring temperature and polarization of this CMB. These experiments have been extremely successful, and in fact, they helped us establish the standard cosmological model. So here on the left-hand side, you can see a little map of the CMB temperature fluctuations, for example, in the celestial sphere. And then what you usually do is to interpret this map, you simply decompose these small fluctuations in the Fourier modes, which are just spherical harmonics in this case, and you can then compute some quantity, which is called the angular power spectrum, which basically is the square of the coefficients of this decomposition in spherical harmonics. And so you find here on the right-hand side some let's say, plot where, as a function of scale, you can see what is the amplitude of different Fourier modes. This power spectrum has a lot of features, and basically these features depend on the initial conditions for our universe, and also on the matter content and evolution of small fluctuations throughout the history of the universe before the CMB forms, also a little bit after, because the CMB propagates through the entire universe to come to us today. And using these features, we can measure cosmological parameters. If you fix some cosmological model and you have a theory of the initial conditions, you can then make predictions for how this power spectrum is supposed to look like, given your cosmological model and cosmological parameters. And then you can simply do the fit to the data to see, first of all, whether your model is compatible with the data, and if it is, what are the values of cosmological parameters and the error bars on these cosmological parameters. And so this is how we do the measurements in the CMB. Now, what we do know is that the temperature information, the temperature of the CMB is almost saturated by the Planck satellite. The polarization experiments are still have a lot of potential to improve these constraints in the future. But we do know, however, that even if we have optimal CMB measurements, there will be many open questions that the CMB alone cannot answer in cosmology. And these questions range from understanding the statistics of the initial conditions and questions related to inflation, for example, many things also in the early universe, and in particular, many questions related to the late universe and the dynamics in the late universe. And for example, a possible non-trivial composition of the dark matter, or like understanding a little bit better the accelerated expansion of the universe and so on, cannot be done with the CMB alone. And so we have to look elsewhere. There are more things to observe than just the CMB. If you think about us sitting today and observing things on our past light cone, which is illustrated here, the CMB is only a single slice. And in principle, we can observe the entire volume of our light cone. There are more things, many more things to see. However, these things are a bit of a different type. And usually these are galaxies that we can observe. Those are some sparse points in space, which are bright enough to see them. And here what is shown is some kind of a galaxy map, of course, shown on our past light cone. And as you can imagine, as we go further back in the past, there are fewer objects to see. But however, still there is a very significant volume of the data that we can collect. And there is a big observational program for this decade with various types of cosmological surveys, which are already operating or starting very soon, that are going to really collect a humongous amount of data, much more than we had in the past. This is one example of how these maps look like. And when we talk about large-scale structure that I mentioned at the beginning, we're talking about these fluctuations in the number density of galaxies, let's say, on scales larger than typical intergalactic separation, which is a few megaparsecs, okay? So you should imagine that we're talking about basically these little waves in the distribution of galaxies. And this distribution, of course, is not random, it's not uniform. And these fluctuations reflect the whole history of the universe, and they're indeed related to the small fluctuations in the CMB. They're just evolved version of these initial fluctuations. And distribution of galaxies in space remembers, in some sense, the initial conditions and the history of the universe. So it's not completely random. So on very small scales, of course, within one galaxy and so on, there is a scrambling of matter and things are very chaotic and you cannot reconstruct anything. But if you look on these cosmological scales, on these large scales, this structure on large scale still remembers the initial conditions and the evolution in the early universe. And this is why we can use these observations to say something about things that we are interested in cosmology. Now, we have been very successful in making these maps. I'm focusing here on the so-called spectroscopic galaxy surveys. Spectroscopic means that we are measuring spectra of individual galaxies, allowing us to measure direction and distance, so that we can make these 3D maps. So these surveys have been happening for many decades now. And here I'm plotting, I'm showing some cartoon with some estimates of what was the number of galaxies in a sample, in observations, as a function of time. And you can see that we are in a nice exponential curve where roughly the spectroscopic sample increases by a factor of 10 every 10 years, okay? So you have already seen, I think, last week, that some results from DESI, which is a currently ongoing spectroscopic survey in the US. There is also the European mission, Euclid, which is also collecting the data. And there are already planned plans and proposals for the so-called stage 5 spectroscopic survey, which will happen next decade, most likely. And so you see this program is basically is a continuation of a long tradition. And maybe the reason why I didn't hear much about it, I think, is also shown in this plot. And there is this very special moment of time now where basically these spectroscopic surveys are catching up with the CMB. And in principle, they by themselves have a similar amount of information as the cosmic microwave background observations. So in other words, if you take the Euclid or DESI data and you do the cosmological analysis without using the CMB, you should find similar type of error bars on cosmological parameters. This is an extremely interesting point in time. Because
sorry,
yes.
Marko, can I ask? Yeah, just wondering how were you quantifying information in the CMB? This horizontal line is just a number.
This is like I'm going to show one plot in a few slides, which hopefully clarify what this means. This is extremely, of course, vague, and it's not clear what does it mean. But I will show a slide which hopefully clarify this. So. So what I wanted to say is that, yes, we're in a very special moment of time where this is becoming very interesting because when we have two similarly powerful probes, first of all, we can check if they're consistent. And on top of that, in combination, they're much more powerful than each individual one. And so this can help us to either really measure lambda CDM cosmological parameters very precisely, or if there is any inconsistency or deviation, discover new physics. And so this is why these times are super exciting. So now there is, of course, one big difficulty that these maps, where we make maps of galaxies, are a bit harder to interpret than the cosmic microwave background radiation observations. So the reason is that, of course, unlike the CMB, where all the physics is linear and also well understood, the galaxy formation and galaxy clustering is much more nonlinear, and there are various effects to be taken into account. First of all, under the influence of gravity, the fluctuations grow. There is this so-called gravitational collapse and so on. Then there is a galaxy formation physics, which basically tells you, given some initial conditions for let's say, a dark matter halo, what type of galaxies can form inside. And this includes all kinds of baryonic physics, complicated astrophysical processes, and so on. We observe things in redshift space. So for those of you who are familiar, there are also these redshift space distortions. It is not so important. So if you don't know about it, don't worry. But there are all kinds of nonlinearities which basically make the description of this nonlinear density field in the late universe very challenging. So, however, to interpret this data, you see, we absolutely need some theoretical description of this field for us to compare our theoretical model to the observations. And in principle, there are two ways forward. One is to solve the full problem, really to simulate the entire universe, including all of these details, using some very advanced hydrodynamical simulations. And let me say immediately that even though this is the full solution in some sense, at the moment, it is not feasible. It's simply numerically too challenging, and there are so many uncertainties in the galaxy formation process that this is not the way that we do cosmological analysis at the moment, and probably we will not do it this way in the foreseeable future. And then the next best thing that we can do is to try to solve this problem partially, focusing on regions of, let's say, parameter space where we can do something analytically. So as I said, this dynamics is nonlinear, but it is not equally nonlinear on all scales. For example, on small scales, when you form a galaxy, everything is very complicated and you cannot describe this process analytically. But on very large scales, these fluctuations are still small. They do evolve, but not so much. And there is a regime where fluctuations are small enough that we can do something. Even the nonlinear process can be treated perturbatively. And perturbatively here means in terms of the amplitude of these fluctuations in the density field. And the whole point here is that on different scales, this amplitude fluctuation is different. So on large scales, fluctuations are still small, relatively small, and they can be treated analytically. On small scales, fluctuations become large, and there we cannot do anything. But so the question is, like, if you want to focus, let's say, on large scales, what can we do? And is this useful for anything, and is it good enough? So even if you want to talk only about large scales, there is still this question, how do I describe these waves in the galaxy number densities on large scales through some theoretical framework? And people have been asking these questions for a very long time, until, let's say, 10 years ago or so, a little bit more than 10 years ago now, there was this idea to actually treat this, if you want, material that exists in our expanding universe, which is made out of dark matter and baryons forming galaxies, basically treat it in some effective way, using the approach of the effective field theory that has been so fruitful in physics. And the main logic here is that we should not try to start from small scales and ask how galaxies form and so on and so forth, in order to be able to describe the long wavelength physics, but the other way around. We should be ignorant about what is the microscopic physics in some sense, and talk only about what is the possible dynamics for these fluctuations on large scales based on symmetries and some general principles, such as the equivalence principle, for instance. And this is very similar to what happens in fluid mechanics. And indeed, the description of this, let's say, cosmological fluid is in some sense similar to the usual fluid hydrodynamics, but it has some peculiarities. For instance, in this cosmological setup, this material is pressureless, so you can squeeze, for example, dark matter as much as you want without producing significant pressure. For example, there are long-range forces which are not screened, and the gravity, which played a fundamental role. So it's a self-gravitating system in an expanding universe. It doesn't have pressure, so there are no sound waves propagating. So there are many peculiarities, and yet you can describe all this using these methods of effective field theory. And so, like in any effective field theory, there will be some relevant degrees of freedom on large scales. In this case, this is only this density contrast, delta G for galaxies, which is basically tells you what is the fluctuation in the number density of galaxies compared to some mean number density of galaxies. The equations of motion are going to be fluid-like, including gravity, and you have to impose all kinds of symmetries that are present there, including equivalence principle. And there will be two expansion parameters. One is the simply fluctuations of the in the number density itself, because as I said, on large scales, this is a small, productions are small, so the typical variance of the density field is small, and this is one good expansion parameter. And the other expansion parameter, like in many FTs, is are derivatives. So we can put more derivatives, let's say, on the various nonlinear terms, and this way you get, let's say, higher order terms in the equations of motion, or what would be equivalent higher derivative operators in quantum field theory. And the importance of this, the main, let's say, advantage of this description is that all UV dependence, in the language of quantum field theory, if you want, all microscopic dependence is in a few parameters in your equations of motion, or your Lagrangian, if you want. And you can actually describe the long wave density field order by order in perturbation theory. And this gives you a universal description of galaxy clustering on scales larger than the cutoff of this theory, which is called nonlinear scale. Okay, so this is a very rough idea. There was a question, maybe?
Yes, I'm just trying to parse it, but maybe the person wants to just ask. So actually, Misael, if you want to unmute and ask directly, or I can read it. Let me see. So oh, I think you're gonna get to this. This is about kind of the comparison between forward modeling and traditional endpoint correlation function. I think this
yes,
is
I will come to that. Yes,
yeah. Let's keep that question for later.
So I'm not going to go into any technical details here, because now there will be a whole talk about how does this work in detail. I just want to say that once you have these equations of motion, we don't talk about Lagrangians here because it's not very useful. It's not a useful language, but directly you can do these things at the level of the equations of motion. The equations of motion will have some nonlinear terms, which are a given order in perturbation theory, and derivative expansion is a fixed number of terms. They have some free coefficients, as in any EFT, that you have to fit from the data. And once you have these nonlinear equations, you can solve them perturbatively. Perturbatively means solve them in terms of the initial conditions, which are very small. The nonlinear fields are going to be like some kind of a convolution of the initial conditions. And you can then compute various correlation functions. For instance, I'm just plotting here the 2-point function, for example, for matter, the simplest possible thing that you can do. And you can see in this little plot that, for example, on very large scales, the 2-point function is basically the same as in the linear theory, which doesn't involve any nonlinearities because fluctuations are very small and nonlinearities are small. And as you go to smaller scales, which I remind you, in Fourier transform means higher k, then you start seeing some significant amount of nonlinearities. And the idea here is that I can describe my density field more precisely than just using simple linear theory, pretending that nothing happens but the linear evolution. Now, it is important to have this better description because there are many more Fourier modes with a little bit higher wave numbers. So in principle, you get a lot of signal. You can describe your density field at a little bit smaller scales in real space, or a little bit higher Ks in Fourier space. And in Fourier space, an important expansion parameter really, which controls the size of the nonlinear correction, is this variance of the density field, delta square, which is just some integral of the linear power spectrum up to some cutoff. So, but anyway, for those of you who are maybe familiar with this should look, just a reminder. If you don't really understand how the whole thing works, for what I'm going to say for the rest of the talk is not super crucial, but just keep in mind that there is a simple analytical basically approach where you can start from the initial conditions, evolve them perturbatively, and take into account nonlinearities on large scales at least, without, of course, being able to do nonlinearities on small scales. This is always outside of the regime of validity of the CFT. Now, galaxies are more complicated, and they have more free parameters. I'm showing here, for example, the bottom, what are the parameters needed to do some leading order corrections to the linear theory. So there are cosmological parameters, of course, but then there will be a bunch of nuisance parameters called counter terms, galaxy bias, maybe you've heard these words. Those are some parameters which basically tell you how to relate the matter distribution and then the number density of galaxies. These are not one-to-one. And there are some free parameters which we have to feed from the data. All right, so So I think that in the last couple of years, one important development was that all of these like results of how to compute things, what is a consistent description, and so on and so forth, were put together in several publicly available numerical codes, which actually do all the computations for you, given some linear power spectrum. And basically, these publicly available codes are similar to what CMB fast, CAMB, or class were for the CMB. So basically, given a cosmological model, now you can run everything and make predictions for the whole light cone if you want. And in some sense, using some theory, which is some kind of a weakly coupled theory, some perturbation theory, all the way from the Banach-Davis vacuum inflation until today, including galaxy fluctuations. So there is a full evolution of fluctuations in the entire space-time. You can compute the observables on the light cone if you want, and you will be able to then make theoretical predictions for any cosmological model. Now, this is very important because it allows us then to really efficiently explore this data and basically compare this data to various theories. And this is what has been done as soon as all this machinery was developed. There were many different analyses in the last couple of years. I will just show one example because I don't want to go into too many details about what can you do with this data. But the conventional analysis is somewhat similar in logic to the CMB. So basically, what we observe in the data is some kind of a galaxy map. Okay, so it is a map where we have a bunch of galaxies in space. Let's simplify it and put them in a simple box. So we have some density fluctuations in the number of galaxies in the box. What we can do then is to do a simple Fourier transform. And then again, like in the power spectrum, take these Fourier coefficients and make the power spectrum, okay? So what is shown here on the left is some power spectrum for the BOSS data, the best galaxy survey that we have at the moment with the publicly available data. The reason why there are several spectra is because of these redshift space distortions that I mentioned. So in principle, these redshift space distortions, if you remember, introduce some anisotropy in the two-point function. And so you can expand this anisotropy in Legendre polynomials. And these different spectra are just different Legendre polynomials of this expansion. But for all practical purposes, you can just think of, if you want, even of this even as a single line. So there is like some two-point function that you measure. This two-point function, as you can see, or the power spectrum, it has features similar to the CMB. There are small BO wiggles. You can maybe see them in this blue line. There will be a quality scale. There will be many similar things to the CMB because, as I said, galaxies remember these initial conditions. Their distribution is not random in space, but these fluctuations remember what was happening in the early universe. And once you have this data, you can proceed in the exactly same way as in the CMB. You can literally then take any cosmological model you want, make predictions using this effective field theory, and compare to the data, okay? And so this is what is called the full shape analysis of the power spectrum. Interestingly, no cosmological parameters, but you measure all cosmological parameters without any input from the CMB. No input from the CMB is needed at this stage, okay? So this is important because you can see you can do some independent measurement and then see, for example, do you get the same results as in the CMB? And in one of the first analyses that we did already in 2019 now, this is exactly what we did. And so you can, for example, look at this contour plot, which shows you what is the posterior for various cosmological parameters, given the data. So the Planck results are these red contours. And then let's say we can look at the blue contours, for instance, or gray contours for the various choices in the analysis for the BOSS data. And you can see that some parameters, such as the amplitude of initial density fluctuations measured to this parameter sigma 8, are much better constrained through the CMB, and that is true. But some parameters, such as capital omega matter or the Hubble parameter, the error bars are similar. And so you see, you have two independent measurements, which are done at very different epochs in the history of the universe, very different systematics, very different data, very different theory. And they agree rather well. And this is, I think, a very, very encouraging result. And it shows us that we can actually do very well with these galaxy servers. And there's some interesting things to be said even with the current data. And things will improve much more in the future.
Sorry, Marko, can I ask, do you have to assume flatness, or are you allowing flatness as a free parameter also? And I thought you might need to see.
Here, flatness is assumed. There were papers where you also vary omega k, and you find similar results because internally the various redshifts can break the degeneracy between omega matter and
I thought you might need to
the BAO basically plays the role of breaking this degeneracy, unlike in the CMB where it's very strong.
Okay, thanks.
Now, coming back to Daniel's question, let me just show you how are things going to look like in the future. So this is some forecast focusing on neutrino mass in particular, which shows you like several contours. It's a little bit of a busy plot, but let me don't look at everything. What is important here is that this is analysis done on a synthetic data. So how the data would look like for the CMB if neutrino mass was 0.1, sound neutrino mass was 0.1 electron-volt, and what you get are these dashed blue contours. That would be the CMB analysis for something like Planck-like survey in this synthetic universe. And then you also make synthetic data for what DESI or Euclid are going to observe. And if you do this two-point function analysis, this is these red contours, okay? So what I meant when I said that there's a similar amount of information at the beginning is that the sizes of these contours are not so different for most of the cosmological parameters. There are some things that CMB measures much better, of course. There are some things that large-scale structure measures better, but on average, these contours look similar. And so if you look, for example, at one of these squares, for example, where there is a small omega CDM and Hubble parameter, you can see that these contours have similar size, but they have different orientation. And the solid blue like contours are what you get in combination of the CMB and large-scale structure. And you can see a humongous improvement. So it is not just a square root of 2, but because you have these different degeneracies due to the fact that you're observing things at very different redshift, and you're sensitive to cosmological parameters in a different way, then the combination of these data sets is going to be far more powerful than each individual data set by themselves. And this is quite interesting because any little breakdown of lambda CDM will show up in combination much more than in individual data sets, okay? So this is how our results are going to look like when these currently ongoing galaxy surveys finish in a couple of years. So you don't have to wait very long. This is coming relatively soon. So Daniel, I don't know if this answers the question. Basically, this is what I had in mind.
Yeah. I just wondered how you even put it in the plot as the number of modes or something like that in the CMB.
Yes, I think that the number of modes is a bit misleading. I think that the number of CMB modes is roughly, let's say 10 million.
Yeah.
These surveys are going to have many more galaxies than that. But then not galaxies and modes do not count 1-to-1. So there is some factor in between. And I think that roughly speaking, it's a factor of 10. So this is where this line is.
Okay.
And I think that more meaningful thing is when you see these error bars, they look kind of, the volume of this kind of comparable. So, all right. So this is basically some recap and review of what are people doing at the moment. So in cosmology, as I said, there was a CMB. The two-point function there gave us a lot of information about our universe. Now we can do the same game in the late universe. We observe the distribution of galaxies in space. We need some theory, and there was this interesting development with this EFT to describe this. But then we do the same thing. We can measure the two-point function. We can fit the data, and basically we see that we recover some cosmological parameters, and we can proceed this way. However, in the last maybe 10 years or so, there has been a lot of development in trying to do things in an alternative way. And I wanted to also say a few words about this. This is supposed to be the main topic of this colloquium. But before I move on to this so-called field level inference, are there any questions about this previous part?
Yes, I have a question. So you were saying that you were talking about the different expected measurements for the different parameters, no? What is expected for like the Hubble constant and the sigma 8 for this Hubble tension? Do we expect that this Euclid or DESI measurements will like alleviate, like make this tension lower or something, or with the
Well, first of all, like well, as I said, this is the measurement from BOSS. You find that Hubble parameter is with smaller error bars, actually, is compatible with what CMB finds. This is not a big surprise, even though the data come from the local universe, if you want. The way that you obtain this Hubble parameter is not a direct measurement, like supernovae or some other, let's say, strong lensing measurements. This is an indirect measurement where you have to solve anyway from the entire history of fluctuations, put them on the light cone, as I said, and then compare to the. So basically, this measurement of Hubble, even though you're looking at the galaxies, depends on the initial conditions, it depends on the early universe physics, and so on and so forth. So this can be done only within a given cosmological model. I think that this is a lambda CDM here, and so within lambda CDM, CMB and galaxies agree. We have tried also to do measurements of other examples, like for example, early dark energy or other types of proposed models. And when you add these large structure data, they do not, usually these models get more constrained, and there is no way to go all the way to the supernovae. So whatever we tried beyond lambda CDM in this combination simply doesn't seem to work. It may be that there is some exotic model which actually does work, but I don't know. And now, importantly, when you look at the future projections, you can see that the Hubble parameter will be measured at 0.1% precision. So imagine that you have some full DESI and CMB, you do the analysis, and you find that lambda CDM fits everything very well, and you have like a very tiny error bar on the Hubble parameter. I think that it will be close to impossible to find another cosmological model, which is in terms of these small error bars, 100 sigma away, which is needed to explain the tension. So it seems to me that either these measurements will move the Hubble parameter to be a bit higher, or there will be some tension between CMB and large-scale structure. But if they agree, and if there is nothing beyond lambda CDM, I think that it will be very hard to then do anything about this, because this is simply going to be very difficult to move. That is my view. So it will not resolve the problem, but I think it will be very difficult to speculate that there is something wrong with the CMB or large-scale structure, because the error bars will be just too small.
I see. Okay, thanks, Marko.
Yeah, no problem.
Okay, sorry, Marko. I guess it is strengthening the case that there's no systematics in the CMB, no? Because you have an independent measurement of.
Yes, I think that in this plot, what you see is that the only thing I can conclude from here is that there is no obvious problem in either of the two, unless you were very lucky that this you cannot rule out, that maybe there is two independent systematics which accidentally coincide. That may always be the case. But if you don't believe in this coincidence, I think this shows that there is no obvious error in the CMB. So doing the lambda CDM analysis in both examples gives the same answer. So then the question is lambda CDM the correct model to fit? And I think that with smaller error bars, if everything fits, it's getting harder and harder to imagine that it's something else. This, I think, is the fair statement.
Okay.
All right, so let me now finally talk a little bit about this field level analysis, which in spirit is a bit different, and it's a much more ambitious approach. So first of all, let me explain what is the question, what is the problem. So there is this problem in cosmology, these questions we always ask, and the question is like how to optimally extract information from the maps. So we make these maps where we have either the CMB fluctuation or some distribution of galaxies or whatever other tracer we observe. And then we want to ask how to get all the information out that is possible to get out. Now, in the case of a field which is a Gaussian field, and we know that our universe, the initial condition is very close to be a Gaussian. Perhaps there are small deviations from these so-called primordial Gaussianities, but these are very small. So to a very good approximation, the universe is Gaussian. And if the field is Gaussian, like the one in the CMB, then it is a theorem that all the information that you can get is in the two-point correlation function. So this is why the CMB analysis is almost optimal using just the power spectrum. You don't have to, for example, compute the three-point function because we know that it will be zero up to, again, this very important but very small primordial non-Gaussianity, possible contribution from the primordial non-Gaussianity. So, so then the task is very simple there. I mean, the Gaussian fields are relatively easy. But as I told you, the nonlinear evolution in the late universe, because you have gravitational collapse, you have the non-trivial formation of galaxies with populated dark matter halos, and so on and so forth, the field that we're observing in the late universe is far away from Gaussian. Of course, on very large scales, where the fluctuations are small, it is approaching Gaussian, of course, because everything is basically linear and it reflects the initial conditions. But as you go to smaller scales and the nonlinearities become more important, things are getting more and more non-Gaussian. And so then the question is, like, how do we take this into account? What is the correct way to do this analysis? What are the optimal observables? What should we do? How to define the likelihood in this case, and so on and so forth. So these are like, likelihood just means how to compare my data and theory, how much weight to give basically to different Fourier modes, different observables and stuff like this. So it's it is like a much more difficult problem. And one idea, which I think we know basically that it must be optimal, even though it is a very hard thing to do in practice, is the following. Do not try to make a compression of your data. Do not try to find some summary statistics, like the two-point function, or whatever else comes to your mind. So take the data as they are, take the whole map, if you want Fourier modes or pixels in real space, and use these simply as the input for analysis. Try to use this as a data, basically raw data without any compression or post-processing, because every compression or doing some summary statistics may lose some information, okay? So the question then is, like, how do I compare my theoretical prediction to this data? Well, I have to take now I have to make the prediction at the map level. I don't want to predict only the two-point correlation function. And so, again, making the prediction at the map level in principle can be done starting from some initial conditions and using, let's say, full hydrodynamical simulation. But that is extremely expensive. And again, it's not feasible at the moment. However, the same perturbative methods that I was describing before do not only allow you to compute correlation functions, but actually fundamentally what you're computing is some nonlinear field before you put the expectation value to compute correlation functions. So there is a so-called perturbative forward modeling where you can really start from the initial conditions, apply this perturbation theory nonlinearities, and predict the nonlinear field at the map level, order by order in perturbation theory, okay? And this is called perturbative forward modeling. And now I think that there was a lot of literature and many papers. Here I'm showing just some references, like original references, but much more development came later, where basically people were able to show that in this not so non-Gaussian regime, where perturbation theory is a still good description, there are big simplifications that this problem has. One is that, of course, this map from the initial conditions to the nonlinear field is relatively simple and easy to put on a computer and all that. And the second thing is that the likelihood for comparing different Fourier modes is Gaussian. It's a very good approximation. So basically, the likelihood is some probability to have observed galaxy density field given some initial conditions delta and some cosmological parameters theta. And Gaussian means that if you take this observed field delta G hat, the difference between the observed field and what you theoretically predict from the initial conditions is distributed as a Gaussian with some noise, which is the variance basically of this distribution. So this delta G without the hat, which depends on delta initial and theta, is your nonlinear model. Okay, so you have to take your nonlinear model, compare it to the data, and you use this likelihood. And this actually can be done numerically. Let me first actually show you, even though I'm running out of time, let me show you basically how well perturbation theory works. There are many papers, again, comparing many different things. There were many tests done and so on and so forth. But visually, you can just see it with your own eyes that things look very good because, for example, what is shown here is one slice from a numerical hydrodynamical simulation with neutral hydrogen, which is much more dense than galaxies. So in some sense, it's harder to predict. And you can see all the filaments and voids and all this complicated cosmic web. There's a snapshot, one slice from a hydrodynamical simulation. And this is what you get when you start from the same initial conditions as the hydrodynamical simulations and evolve things perturbatively, adjusting just a few Gnosis parameters that I was mentioning at the beginning. So going back and forth between these two slices, you can see that all the structure is basically almost the same. There are small variations, but they're compatible with the shot noise, with the fact that you have a discrete number of tracers. So statistically, you cannot tell these maps apart on large scales, meaning like larger than a few megaparsec, okay? So we have today very good, I mean, not only we can compute very well correlation functions, but we also have very easy and simple way to make maps perturbatively. And so once you have this, then you can take your likelihood that I just mentioned in the previous slide, compute the posterior, which is basically the probability for some cosmological parameters theta, given the observed galaxy density field. Using the Bayes theorem, this posterior is just some integral over all possible initial conditions of your likelihood times the prior for these initial conditions, which is just, in here you can see that delta has a Gaussian distribution because it's a Gaussian random field with a linear power spectrum P of k. So you can basically do this averaging of initial conditions numerically. Now, this is a humongous number of parameters. You have to vary the phases and amplitudes of each Fourier mode in your initial grid, evolve it for every point in the Markov chain, compare to the data using this likelihood, and compute the posterior. So you keep doing this, and even though you have 10 to the 6 to 10 to the 9 parameters, people are actually able to do these things these days numerically. This is an amazing progress using artificial intelligence and very efficient samplers like this Hamiltonian Monte Carlo sampling and so on and so forth. And then it is very interesting because this is, you see, it's a very different approach. You're not computing endpoint functions and comparing to the data with the usual covariance matrices and so on and so forth. You're really trying to fit the whole map in one go. And the question is, like, do you get something more or something less than in the conventional analysis? And what is our expectation actually for these things, okay? So let me show you some results. There are not that many results doing some cosmological analysis because this method is still being developed and tested. But in some cases where there were comparisons between, let's say, standard analysis based on, let's say, power spectrum, the 2-point function or the 3-point function by spectrum, and this field level inference, the results show that there is a big improvement when you do the field level inference. So, for instance, the upper plot is a result from a recent paper with many authors. It is like this beyond 2-point function collaboration, where people were exploring how much more information can we get beyond the 2-point function. And you can see here, for example, some analysis in green done with the standard perturbation theory, going to relatively high K-max, using the 2-point function, the 3-point function in combination. So it's like a power spectrum by spectrum analysis, and green error bars are pretty large. The sigma 8, again, is just the parameter which tells you what is the amplitude of the initial density field. Okay, this was the goal of this analysis. Well, if you do the field-based analysis using the EFT method at lower K-max, only 0.1, so you're not going to very small scales, you get much better error bars. Okay, so that is one thing that is a result of this thing. So the bottom plot, there is a separate analysis where basically people took the simulation outputs of very large simulation boxes, they were varying only the amplitude of primordial fluctuations. Again, here this parameter alpha is just how big is the amplitude compared to some fiducial value. So basically, it's the same as sigma 8. It just gives you the fractional, basically, error bar. So you can see that, like, if you do power spectrum and bispectrum analysis of these are dark matter halos in real space, so relatively simple nonlinear density field to predict. The power spectrum and bispectrum analysis, depending on which K-max do you use, is 3, 4, 5 times worse than the field level analysis, okay? And that is the state of the art when it comes to actually trying to do this field level analysis numerically and comparing it to the conventional analysis. Now, I would like to argue for the rest of the talk, if I can take 5 more minutes, maybe or so, why is this so confusing and why is this very unexpected, okay? And I think that it's very interesting to basically maybe go and explore these results in more detail. And I would like to give you some intuition for why things may look here a bit maybe too optimistic. Or if they're true, there will be some radically new idea that we are missing in all this business of perturbation theory. So one or the two will happen. So now to do that, actually, we were already thinking about it for some time. We wrote this paper with Giovanni Cabas and Mattias Lariaga, where we tried to answer this question analytically, without doing things really trying to do it on the computer. To answer the simple question, which is, if I imagine some very simple perturbative setup, where I have some simple perturbative model, in some limit of, let's say, small noise and other simplifying assumptions, because I'm doing perturbation theory, in principle, I can compute the expected error bars from the conventional analysis, power spectrum, bispectrum, and I can compute the expected error bars from the full field level analysis without doing things numerically. So we are exploiting the fact that in the perturbative forward model, one can perturbatively compute what are the expected error bars that you can get once you do the analysis, okay? And so in the simplest setup, you can assume that the noise is basically close to 0. So this will be true, for example, for dark matter. If you do in dark matter, or if you do some traces which are very dense, the noise is negligible. And which is indeed the situation in some of these simulation boxes I showed before. And the second thing that we assume is that the only expansion parameter in our theory is the variance of the density field. So as long as we are staying in the perturbative regime where the fluctuations are small, our results should hold, okay? So then under these assumptions, the posterior simplifies a lot, because instead of having this Gaussian distribution with some noise as a variance between the theory and observations, now you have a delta function. This delta function is in terms of the nonlinear fields. And if you want to get the delta function, if you want to use it, you simply have to include some Jacobian in this computation, and you have to find the inverse model. So given the initial conditions, you can predict the forward model, but also because it's perturbative, you can invert it very easily. And then you can compute the posterior analytically. Once you have the posterior, it's very easy to understand what kind of error bars do you expect from this posterior. So here I'm just showing that under these assumptions, the perturbative forward model will be very simple, just some convolution of the initial conditions. And the inverse model will also be perturbative, where these basically kernels which tell you how to convolve the nonlinear field to go back to the initial conditions can be simply computed from the perturbative forward model. So things are very simple. If you do this math, if you do this analysis in this limited setup, you will find the error bar from the power. Let me say, as an example, the first example where something non-trivial happens is where you have the so-called linear bias, and you want to measure the amplitude of the initial conditions. This linear bias is just some linear parameter telling you how the Gaussian density field is related to the matter field. And at first order, in linear theory, the bias parameter and amplitude are perfectly degenerate, so you cannot tell them apart. But then the nonlinearities break this degeneracy. So the common law is that if you include higher order endpoint functions, you will somehow break the degeneracies better. And one intuitive explanation for these results at the field level is that you're getting a lot of information from some higher order endpoint functions that you're usually not taking into account into the power spectrum or bispectrum analysis. So what we did then is to compute like what are the expected error bars on the amplitude when we marginalize over this B1 parameter in the power spectrum and bispectrum analysis, and then we compute the posterior for the forward modeling and again find what is the error bar. It turns out that these two error bars are identical. So the expression is shown here. So both field level and P plus B will tell you the same answer, okay? And in this same model, if you do one or the other analytically, you will find the same answer. So more recently, just to make sure that this analytical approximation makes sense, we were doing some tests with Kazuki Kitsu in Japan. And he was basically running this analysis on some more realistic mocks, finding that indeed, as expected, the power spectrum analysis doesn't look very good in this case. But the power spectrum plus bispectrum, which is the blue contour, is almost indistinguishable from the field level contour, which is the gray one. So you can basically barely not tell them apart. And this is what we expect from this analytical point of view and from perturbation theory itself. Because it is true that the field level has the whole map and all endpoint functions, but the intuition is that in perturbation theory, higher order endpoint functions always count much less. Otherwise, you will not be perturbative. And for this reason, if you stay on large scales, which is the case in all these tests that I showed before, the moment you break the degeneracies, for example, in this case, you have to use power spectrum and bispectrum, then you basically get all the information that you possibly can, and there will be nothing more on top of that in the field level analysis. So I think that the situation at the moment is rather confusing. So on one hand, there are various tests and several examples where we see that in a more realistic data, meaning more realistic inputs taken from simulations, there seemed to be a large improvement if you do the simulation-based inference, the forward modeling and field level-based inference. While what we expect from perturbation theory, and this forward model is based on perturbation theory, so what we expect from perturbation theory is there should be no big difference between the power spectrum and bispectrum analysis, let's say, in this setup that was tested so far. So these are very confusing results at the moment. To me, I think it's a big mystery because you see, we would expect identical error bars. What is found in some examples is factor of 5 difference. Factor of 5 is a huge difference. It's not like a 50% improvement. So obviously, there is something that is being missed at the moment. And I honestly don't know what exactly it is. So either the logic that led us to think that the perturbative analysis should be, in perturbation theory, the P plus B, for example, in these examples, is the same as field level, is wrong. There may be some new large parameter that we were missing, which helps field level improve the analysis quite a bit. Or there is something with the field level analysis itself, which is maybe too optimistic or too good to be true. And like the error bars seem to be much smaller, even though they're not supposed to be. I can tell you about different options, how this can be resolved. But either way, whatever is the resolution, I think that we'll learn something very important about either perturbation theory or this field level analysis. And I think it will be very interesting to try to resolve these issues. So anyway, I think that I'm like running out of time, so I will just leave the conclusions here. Essentially, in this talk, I didn't go into many details. I didn't show you some nice maybe calculation, but I wanted to give you a little bit of an overview of what was happening with this conventional analysis. I wanted to give you some idea about what are people trying to do now with this field level inference. And I wanted to show you what is the current state of the art. So there are some theoretical arguments that tell you one thing, and then there are some real-world examples where people do the analysis which show something completely different. And I think it's an interesting situation where basically we will either, whatever is the resolution, we will learn something And I think that this is a good thing to maybe explore in the coming years. So given the big amount of data that is coming, I think understanding this it will be very, very important. So I stop here. Thank you.
Okay, thank you very much. Thanks for the nice talk. Are there any questions? Both in the room and online. Yeah, now Michelle. I don't know if your microphone now works.
Yes. Greetings from Honduras, Central America. Daniel, Marko, and everyone present. I had the opportunity to read a paper with Cabas and Saldarriaga and to the conference, and I have two questions.
Yes.
One question is, what are the case limitation of perturbative models on non-linear scales?
Yes, this is a very good question. Basically, the question is, you see, when we, for instance, let me go back here. Like when we talk about, I don't know where, maybe what is the best thing to look at, but basically the question is, up to which scales can we trust perturbation theory, and up to which scale our results make sense, okay? I think that the expansion parameter, of course, the answer is never perfect, because whichever scale you choose, if you want to be super precise, there are always some higher order corrections that you're missing. So you have to also specify what is the margin of the error that you want to accept. So for example, let me tell. The main parameter really is this variance of the density field, which tells you how big are these loops that you're not computing, things like that. This is this parameter here. So basically, if you stop, let's say at Kmax 0.1 at some redshift 0.5 or redshift 1, the variance of the density field is a 10% level. So you know that the first nonlinear corrections are 10% of the linear theory. And then the second nonlinear correction will be 1%. It's like 10% of a 10%. So if you're willing to make 1% margin of error, then you can safely use our results at Kmax of 0.1. And indeed, in this analysis, this is exactly what is done. So you see, like the typical Kmax here is 0.1. So, and this is not redshift 0. This is redshift, I think 0.5. Yeah. So basically, at these redshifts, I think that at the K.1 or so, for sure, all of these results should hold. We are in the very linear regime. The nonlinearities are 10%. So this is why it is a bit mysterious. How can a 10% nonlinearity lead to a factor of 5 improvement in the measurement of a cosmological parameter? It's a very counterintuitive thing, and this is why I think this is it's an interesting puzzle. I hope that this answered. Now, of course, if you go to higher K, sometimes in the analysis you see people go to 0.2, 0.3. This is because when you want to do the analysis with galaxies, there is also this shot noise, which is usually very high. So if you go to this higher Kmax, you're basically fitting the shot noise and you don't get any biased answer, but also your error bars do not improve much. So really, which Kmax do you want to use? It depends on what type of tracer you're looking at. Are you talking about the matter or galaxies, and how big is your volume? With tiny error bars, you want to stop a little bit sooner. With big error bars, you can go a bit further. So it is a game of, there's a little bit of an art there, choosing the appropriate Kmax for each particular analysis. But you can estimate how well you're doing using this variance of the density field.
Thank you. And second question is, how does forward modeling optimize the analysis of 10 to DH galaxies compared to traditional methods?
Well, let me maybe say that so it depends. I don't know what is the best place to look at, but if you had like the exact simulation, which is super fast, you can just put initial conditions and it simulates the whole universe with all the galaxy information and everything. Then what you would do is basically to run a lot of these simulations with different initial conditions, with different cosmological parameters and so on, you will learn what type of cosmologies and initial conditions give you what type of answers. And in some sense, you will learn the likelihood itself. So when you compare to the real data, you can then use this likelihood, and you can use, again, this infinite power of computational power to compute everything, match all Fourier modes and all scales and so on and so forth. And you will, in this way, you will get the most optimal possible results, because you see, the conventional method are based on endpoint functions. If you're on large scales in the weakly non-Gaussian regime, a few endpoint functions should be sufficient to capture everything. But as you go to small scales, and these become very nonlinear, then endpoint functions simply break down. You cannot, it's not a useful description. And there, the full forward modeling would be very helpful. But we do not have such machine. Making a simulation is very difficult, which is particularly the precise one. So if you want to do perturbation theory, also in forward modeling, you have to stop at some Kmax, which is 0.1, 0.15, whatever it is. So, so now the question is like, why does forward modeling make something better? I don't know. So I think that here it seems that it does, but I would imagine, but then also there is an argument to tell you that it should not. So it is a bit unclear at the moment what is happening, whether the argument is correct and there is some mistake or some problem with the forward modeling done numerically, or maybe this analysis is correct, but then in our argument for why a forward model should be the same as P plus B, let's say, we are missing something. Mm-hmm. In principle, these forward models always are made with a certain order in perturbation theory. At a given order in perturbation theory, you can compute only a few correlation functions which you can trust. And so somehow it seems that by definition, you should not get more than whatever correlation function you can compute. But this is not what we see in practice. And I don't know. I don't know the answer. Why does it get better? I don't know if this is real or it's some, let's say, problem. For example, one possibility is that the forward model is getting a lot of information from some very high order endpoint functions and gets artificially small error bars. But in the perturbation theory, it's not supposed to do that because you believe it only up to certain perturbative order. Now, when you do the correlation function analysis, you can do things ordered by the perturbation theory. But when you compare the maps, you don't have a way to truncate forward. You cannot tell, don't use 5-point function because I didn't compute. So what you would have to do is to somehow say, there is some 5-point cumulant in the noise, which I have to marginalize over to prevent it from using some very subtle correlations. But this is extremely hard to do in practice. So it is unclear at the moment, like what is happening. But yeah, I don't know. Like it's important to explore.
So let's see if there's questions from anybody else.
Yes. Thank you for answers and nice talk. And your papers, Daniel and Marko, are very fascinating. Cosmology is my passion. For ustedes.
Thanks. Okay, thanks for joining. Yeah. Any other questions? Anybody else? Otherwise, maybe I have one more question because I'm suspecting I'm kind of misunderstanding your final punchline. Because I thought you were demonstrating that somehow if you include enough endpoint functions to break all degeneracies, that the kind of the endpoint analysis and the field level analysis start agreeing again. So I thought you wanted to then say that that's maybe what's going wrong in the
well, I think that what is a bit confusing is that, okay, so here I'm showing that P plus B agrees with the forward modeling. But again, it is in this relatively simple setup which is on B1 and altitude. Now, what was done in this analysis is more complicated. The real halos, which have to be the Lagrangian perturbation theory to displace particles appropriately. They're all higher order bias parameters. So basically, you may say, well, if you include the power spectrum, bispectrum, trispectrum, you will get things right. Now, but there are many, I think, indications to tell you that if you include the trispectrum, you don't gain anything. This is, I think, a known thing. So basically, P plus B again will be more or less everything that you will get. And if this is the case, then it is very puzzling, like what makes this difference. So I don't think that including the trispectrum really can fix this. Because it would mean that the trispectrum can shrink the error bars by a factor of 5. That would be very surprising, because the three-level trispectrum has a bunch of new bias parameters to fit from this amplitude, so it doesn't have much degeneracy breaking power. So it is really it's really puzzling, like how does this work? Because this forward model has a Lagrange perturbation theory. This is fine, but it is only it's correct exactly up to cubic order. So basically, because the biasing goes only up to cubic order, which means that the only thing you can trust from this forward model is the one loop power spectrum, three-level bispectrum, and three-level trispectrum. That's it. So, but then combining all these statistics, I think you will still get large error bars. So,
yeah, I just thought that from your experiment somehow would infer what's going on here, but then somehow.
Well, I think that this experiment is a bit of a counterexample to these results.
Yeah, exactly. It's something.
So then I don't know, like, but then again, we are doing it in a very simplified setup where, for example, there are no displacements, there is no Lagrange perturbation theory. I think that these displacements do not matter because at the end of the day, any field level analysis is a correlation function analysis because you're averaging over initial conditions. So when you do this, because of this equivalence principle, all these displacements will cancel as they do in the correlation function. So this was the argument to say that there should be no difference. But yeah, I think that more tests should be done, but like careful tests, because somehow in these analyses, like you always do the most complicated example directly, and it's never clear. Maybe do one step at a time. Maybe something will be weird. So.
Okay, maybe a last chance for last question, if there's any also in the room. If not, we're already a bit over time, so maybe we stop. Thank Marko again and stop here. Thanks a lot.
All right, thanks.